do a rotational problem. A wheel. I'm going to be back with better markers.
Physics. Oh, by the way, I was the one who moved the chair back. What? Did you feel the wind for a second?
All right. A wheel starts at rest. And rotates for 3 seconds. With a uniform acceleration. Of 9.8 radians per second squared. How much does it rotate? Anyone just want to shout out the answer?
Roughly 44.1 meters.
Ooh, so close. -2.
3.26.
Pardon?
3.266666.
No. This is your issue.
Isn't it exactly the same number?
Pardon?
Isn't it exactly the same number?
It is exactly the same number. The question is, what are the units?
Meters per second.
No, radians.
Yeah, radians.
per second.
44.1 radians.
Not per second.
If you wanted to calculate it, well, the formula is the change in the angle, or the angular displacement, or how much it rotates, is equal to 1/2 times the angular acceleration times time squared. Oh yeah, by the way, the angular analog of time is time, yeah. Oh, that's just, well, good. I imagine, deep inside you're feeling, all right, a little bit more of me is complete. Questions before we take it a little bit further? All right, still going with the analogy here of, or the analogs. Oh yeah, I'm about to ask it. What's the formula for kinetic energy?
1/2 mv squared.
Can't tell it, but I was smiling. All right. Rotational kinetic energy.
One half I omega squared.
All right. It does just work the same way the other ones, where you can just transliterate from one system to the other. But from the video, do you recall, or from class, do you recall why I wanted you to memorize kinetic energy formula? What was special about that one as opposed to any of the others?
Because it states
Yes. But here I am saying there's another formula for kinetic energy, where before I said there's just one. Well, there is just one. This, at the heart of this one, is this. Let me go grab the wheel from across the hall.
Video of a woman spinning a bicycle wheel and then it floats in the air.
All right, sorry. Yeah, it's gonna move. So, I have a wheel spinning like this. First off, what is the direction of its angular velocity? All right, you got two people who pointed in the correct direction. Or actually pointed in a whole lot of directions, so at least one of them is right. No,
Down.
I thought your answer the first time was right. The trouble with saying clockwise is that it
Is
looks
it down?
counterclockwise to me. It's not down,
Oh,
not up. Because you say down, or you had said that way, I guess my left or right. Well, if it's spinning like that, yeah, that is indeed going that way, but down here it's going in the opposite direction. If you went up, down, that's going up, while that one's going down. So saying up, down, left, or right is not really going to help. Clockwise, counterclockwise doesn't work because what's clockwise to you is counterclockwise to me and vice versa. So how do you resolve the direction so that it's very clear which way it's spinning?
from point of view.
Wow, that's a lot already. Remember, physicists don't want to write that much.
We can right hand rule
Could
Rowena, say it again?
We can right hand rule.
Yes, the right-hand rule. If you're left-handed, it's still a right-hand rule. It's not dominant hand rule. How many left-handed people in here? One, okay. Not the dominant hand, it's the right hand. All right, so the way they do that. I got an axle here. There is a point on something rotating like this that's not turning. The axle, not turning. Now, the right-hand rule is I'm going to point my thumb in the direction of, along the axle. The axle's moving back and forth, so my thumb's either going to point towards me or away from me. I want my fingers to curl in the direction that it's spinning. So it's like my thumb is the axle, and if it's spinning like that, I want to curl my fingers like this. My thumb points outwards. If it's spinning like that, again, thumb's the axle, my thumb's either pointing this way or that way. Well, this time it's spinning around like that. My thumb points towards the board. The thumb is the direction of the angular velocity. So when I spin it like this, the angular velocity is that way. Now, when I was first doing physics, that confused me a great deal, because I kept trying to picture something actually going that way. There is nothing going that way. Nothing physically going that way. It is just the convention, because if I said I have a wheel spinning in the classroom and the angular velocity is towards the back of the room, it doesn't matter what your perspective is, it's going to be rotating like that. If you said clockwise, counterclockwise, then you have to throw in, well, if you're in the middle of the room, then it's going counterclockwise. If you're at the front of the room looking towards the back, it's clockwise. That's way too much writing.
So would you just say to the board?
Or, we've done I hat, J hat.
Oh,
We now introduce K hat. Let's go with a traditional I hat going to the right, J hat going up. Again, it's called a right-handed coordinate system. When you put your hands in the direction of I hat, I got 360 degrees of rotation there. Put my hand in the direction of I hat. I want my fingers to curl towards J hat. My thumb points in the direction of K hat. K hat's coming out of the board. This is known as a right-handed coordinate system. That is tradition unless you state otherwise. Please don't. Stick with a right-handed coordinate system. So K hat. So how do I actually represent a third dimension on a two-dimensional board?
Could you write a dotted line, kind of like diagonally towards the bottom left?
Like that?
Yeah.
And oftentimes that's done, whether it's dotted or solid, it depends upon your style. But yeah, I have seen it done that way. And I usually see the solid line, and you're just supposed to picture it's in 3 dimension. But that also could just be a vector down going towards the third quadrant. They came up with something different, of course. If this works for you, great. But many times on the board, I'm not going to draw it that way. I'm going to draw it as if a vector is coming right at you. Here's the convention. A dot, sometimes circled. This is out of the board. Or the surface, whatever you're writing on, it's out of the, I'll just put board in quotation marks because that's what I'm doing, but it'd be your paper. X into the board. Now, some students seem to, get these backwards, and at some point I'm going to write the wrong one. But the memory trick is the arrow. If an arrow is coming at you, you will see the point. If it's going away from you, you will see the feathers. Yes, I know feathers on arrows do not look like that. It's just a memory thing. So away from you is the X, towards you is the point. So the angular velocity, the direction of the angular velocity of the wheel. The last time we did K hat direction. I now take this and I rotate it like that. What is the direction of the angular velocity of the wheel? Right-handed. All right, so we got a whole bunch of people giving me the thumbs up.
Good job.
Or up yours, depending on where you are. It is indeed up. If you did the left hand, and it point the other direction, so it is right hand upwards.
so would it be J?
Yes, it would be J hat.
Okay.
Yeah. There was a 252 test that I gave, physics 252 test that I gave years ago, where there's a whole lot of right-hand rules in it. And so the first part of the test was trying to figure out directions of things. And so there were a whole lot of people doing this during the test. They were looking down and doing this. And it's one of the regrets. I wish I had filmed it and then set it to music. It was like hand ballet. That's back when my test sometimes took 4 or 5 hours. I had to cut it back. Anyway. All right, so getting back to this. If I want to figure out the kinetic energy of the wheel, what speed would you use?
Radians per second.
Pardon?
Radians per second.
All right, that would be my angular speed. But I know the formula 1/2 mv squared. What would you use for v? Or what's the inherent problem with using v?
It doesn't give you direction.
Kinetic energy is scalar anyway, so we don't need direction there.
It doesn't go anywhere? It keeps coming back to the same place?
No, well, it's still going. I mean, it still has a speed. I mean, if that piece of paper ends up back where it started, then its average velocity is 0, but we're looking for speed. All right, let's do it this way then. What's the formula for speed?
Time over distance.
Distance over time.
Yeah. Let's see.
Oh,
Yes?
I think is it because every part of the wheel is traveling a different distance over the same amount of time?
Yes. How would you find the distance? A point right here. How would you find the distance that it travels?
It's distance from the center multiplied by the 2 pi.
It's circumference.
The circumference.
It is circumference. It's 2 pi r. So the distance that it's going to travel depends on how far you are from the center. So that's 2 pi r divided by time. I'll just drop it down to t. So time starts at 0. That's just 2 pi over time times r. Well, if I'm talking about going around an entire circle, that 2 pi right there, that's the change in an angle divided by the change in time times r. And what is that?
Angular velocity.
Yeah, or speed, the way I've written it. Just omega r. So we have a relationship here between the linear speed and the angular speed. If in what's called a rigid body, all the parts of the wheel take the exact same amount of time to go around. So the time it takes, so you take 2 pi divided by how much time it takes, they all have the same angular speed, all parts of it. But the parts further out are traveling faster because they have to go a farther distance. Imagine that we were outside. I'm gonna put the cap down somewhere. There it is. So this morning, I was supposed to take my dog to a groomer because he needs someone who knows how to handle him. And so I started off, and I was almost at the vet's office before I remembered, wait a second, I'm not going to the vet, I'm going to the other place. And so I turn around, and I'm trying to think of how to get there. And ultimately, I go almost all the way back home to get back to the vet because I couldn't picture the shortcut in my head. And that's pretty much the way the day's been going. Alright, so they all have the same angular speed on a rigid body, they just have different distances. So now, I'm gonna simplify it down to, I've got overhead view of a door, this thing is gonna swing. I want to figure out what the kinetic energy of this thing swinging is. But I'm not quite sure what speed did it go, because if that's my pivot point, or if it's a door, it's a hinge probably. I know I want to do 1/2 mv squared. Well, mass I'm fine with, but I still have this issue with speed. So if I break it in half, I can still use sort of that center point to find the speed at that point, and it's a better approximation. Or I could break it up even more, or, ultimately, I want to break it up into a whole lot of tiny little pieces and then use the speed for each of those. So I'm just gonna number them as piece 1, piece 2, piece 3, and so on. So this would be 1/2 the mass of piece 1 times the speed of piece 1 squared plus 1/2 times the mass of piece 2 times the speed of 2 squared plus however many I break it up into. I break it up in n pieces. So that's just one way of writing the fact that I'm just going to break this up into a whole bunch of tiny little pieces and then find the kinetic energy of each of those tiny pieces and then add them all up. But as you should all know at this point, that's too much writing. So the math people came up with a way of expressing a sum of adding a bunch of things together. So they put this symbol in front that says, I'm going to add a bunch of stuff together. 1/2 m sub I v sub I squared, where I is equal to 1 to n. I've circled it to separate it. This basically says you first put I is equal to 1 in there, plus, then you put 2 in there, plus, then you put 3 in there, and so on, until you get all the way up to this number right here, whatever it happens to be. So my kinetic energy, space. So my kinetic energy of anything that's rotating is